Welcome to This Explainer. Today, we're tackling a massive, totally mind-bending question about our place in the cosmos. Every time we look up at the night sky, we're essentially confined to a tiny, localized neighborhood of stars. But human curiosity, well, that knows absolutely no bounds. So today, we're asking the big one. Are we destined to stay here in our galactic backyard forever? Or could the laws of physics actually hand us a key to the greater universe? Let's find out.
Okay, let's map out our journey for today. First, we'll talk about the vast distance of the universe. Then, we'll dive into Einstein's shortcut, explore the mind-bending concepts of wormholes and dimensions, and finally, we'll look at the practical challenges standing in our way.
Section 1, the vast distance of the universe. To kick things off, we really need to humble ourselves before the true scale of the cosmos. So, will mankind ever leave the Milky Way? It's a question that pushes the very limits of human capability. Right now, we have these incredible telescopes that can peer at planets hundreds of light years away, but physically packing up and leaving our home galaxy, that is a completely different story. Think about the number 93 billion. That staggering figure represents the observable diameter of our universe in light years. Just let that sink in for a second. If you were traveling at the absolute speed limit of the universe, the speed of light, it would literally take you 93 billion years just to get from one edge to the other. Let's bring this a little closer to home to put it in perspective. Our nearest galactic neighbor is the Andromeda Galaxy, which is about 1.5 million light years away. If we launched a spacecraft traveling at 28,000 kilometers per hour, which is pretty much the peak of our current technology, it would take 94.5 billion years to reach Andromeda. That is just mind-boggling, especially when you remember that our own sun is less than 5 billion years old. And hey, even if we magically built a ship that travels at the speed of light, it would still take 2.5 million years to make the trip. So traveling conventionally through space? Yeah, that's just not going to work for us. Section 2. Einstein's shortcut. Since moving straight through space is basically a dead end due to the sheer time involved, we have to bend the rules of space itself. We need a cosmic loophole. To cross billions of kilometers in mere minutes, we'd need a wormhole. A wormhole is basically a theoretical cosmic shortcut connecting two incredibly distant points in spacetime. If you've ever seen the 2014 movie Interstellar, this is exactly the kind of shortcut they use to jump across galaxies instantly. But the coolest part? This isn't just Hollywood magic. It's deeply rooted in real, heavy-duty physics. The history here is actually amazing. It all started back in 1915 when Einstein published his 10 field equations of general relativity. Just a year later, in 1916, Carl Schwarzschild calculated a solution to those equations that predicted black holes. Fast forward to 2019, and boom, humanity actually captures the very first photograph of a black hole, proving that math right. But here's the best-kept secret. Just like a quadratic equation can have two answers, Einstein's equations have a second mathematical solution, and that second solution is what we call an Einstein-Rosen bridge, a wormhole. To wrap our heads around this, we have to look at how Einstein viewed the universe. Picture space and time as a giant, flat bedsheet. When you place a heavy sphere right in the middle of it, the sheet dips, right? Mass and energy literally cause the space and time around them to shrink and curve. And the heavier the object, the deeper that curve becomes. Section 3, Wormholes and Dimensions. Now that we have that bedsheet in mind, let's visualize this famous Einstein-Rosen bridge and see how extra dimensions give us that desperately needed shortcut. Imagine taking a flat piece of paper and drawing two dots on opposite ends. To travel between them normally, you'd have to trace a long line all the way across the page. But what if you just fold the paper so the dots touch and then poke a pen right through both? You've just created a bridge. By folding the actual fabric of space, a wormhole acts just like that pen, instantly connecting two points that used to be light years apart. Think about it like booking a flight from New York to Sri Lanka. On a flat 2D map, a straight line makes it look like you should just fly directly over Africa. But that's a total illusion created by the flat surface. Grab a 3D globe and you realize the actual shortest path curves up north over Europe. Just like using the third dimension changes your flight path, tapping into a fourth dimension completely redefines the shortest path through the universe. Now, if we ever actually encountered a wormhole, it wouldn't look like those flat hourglass shapes you always see drawn online. Since we're 3D beings, a real wormhole would look like a 3D sphere from the outside.
And if you were brave enough to fly into it, it would act as a sort of connecting tube. From inside, everything around you would look severely curved and distorted.
Section 4. Practical challenges. All right, time for a reality check. Because theoretically, crossing these cosmic bridges comes with some absolutely extreme dangers. We can't exactly just pack our bags and jump in. First off, the gravity. It would be intensely crushing. The entrance to a wormhole essentially acts exactly like a black hole, pulling everything into its massive gravitational well. The really terrifying problem is that if the exit also acts like a black hole, the gravity pulling you back inside would be so strong that you'd need to travel faster than the speed of light just to get out the other side. And since nothing travels faster than light, you'd literally be trapped in the throat of the wormhole forever. No thank you.
So, how do we survive the trip? Well, scientists theorize that the exit door has to act as a white hole. In physics, there's often an exact opposite for every phenomenon. A white hole is the absolute opposite of a black hole. A black hole traps everything inside, but a white hole violently pushes everything out, and absolutely nothing can enter it. For a wormhole to actually be traversable, one end pulls you in, and the white hole end pushes you safely out into a brand new galaxy. But yeah, there is a major catch. White holes haven't been conclusively proven to exist. Some scientists actually thought they spotted a white hole event back in 2006, but it's still super heavily debated today. A lot of experts argue that white holes might work perfectly on a chalkboard, but are physically impossible in the real world. Because of this, white holes and fully functioning natural wormholes remain a massive roadblock in theoretical physics.
But hey, don't lose hope just yet. Cutting-edge lab physics has actually managed to mimic these effects recently. In 2015, a team of brilliant scientists successfully created a magnetic wormhole right in a lab. They used advanced magnetic fields to invisibly tunnel a magnetic signature through space. Now, sure, it's not the giant space-bending tunnel we need for a starship, but it proves that the foundational mechanics are actually scientifically possible. The dream is very much alive. So the universe is mind-bogglingly vast, and time is our biggest enemy. But Einstein's equations cracked the door open, and modern physics is slowly figuring out how to pick the lock. If we can ever harness these theories and survive the extreme gravity, traveling beyond our galaxy might just be a matter of time and human ingenuity. So, what do you think? If the universe really does hold these hidden shortcuts, when will humanity finally be ready to take the leap into the unknown? Thanks for hanging out and exploring with us on this explainer. And remember, keep your eyes on the stars.